These are the notes for target 1 in the electricity and magnetism unit. And the target says that you can apply conservation of charge to model the behavior of electrically charged objects. So what this target does is it sets up some just extreme basics about electricity that we need to know before we can apply it to circuits and things such as circuits in terms of alternating current, direct current, wiring, that sort of thing. So charge conservation. Okay, one of the first things that we've talked about over and over is what conserve means in physics. And if you're in class, you see this note card where it says, how are electrons being conserved in the simulation? In order to do that, you need to click into Moodle, and there will be a simulation that has to do with balloons and sweaters. So you know where the unit is at in Moodle, and there will be one about sweaters and balloons, and then the one underneath of it is John Travoltage. Very clever. All right, but what you notice is if you're in the correct spot, you rub the balloon on the sweater and you see some things happen. All right, so it's this idea of conserved. What does conserved mean? And what we should know from the energy unit, so energy conservation or momentum conservation, is that the number stays the same. We know that that's what it means in physics. So this number of charges has to stay constant, has to stay the same. And in this target, we've got to set up some basic rules. So the law or rule of electric charges says something like this. If you have a positive charge and a negative charge, if you have an oppositely charged objects, one is positive, one is negative. If you have a proton and you have an electron, these two things will be attracted to each other. I always joke about the cheesy Hallmark movies where opposites always attract and everybody lives happily ever after. So if you have two of the same charges, like two negatively charged objects or two electrons, they would not attract. Same as if you have two protons or two positively charged objects. These would repel. They would push away from each other. And that's what this law says, is that opposite charges attract, the same charges or like charges repel. So if you were in the simulation, you've seen how electrons can move around. And I'm not going to draw a sweater, but most of us have done this as a kid, where, wow, that person's got a big head. But you get a person, and they're going to have some good hair here. All right, so here's our person. And there we got some awesome, sweet-looking bangs, too. And you take a balloon that normally would have equal numbers of charges. So for every positive, there's a negative. For every negative, there's a positive. So if I have 3 positives, there would be 3 negatives. You take that balloon, and you rub it on somebody's head. And we've all seen this phenomenon, and it causes their hair to stand up. Okay? So how does that happen? What's happening? If you've ran the simulation on Moodle, then you know that electrons move back and forth. The negative move back and forth. So electrons, in this case, move to the balloon. So normally, as you're sitting there today, your hair is probably not sticking up unless you intentionally made it stick up. So for every proton, there's an electron. Your hair is pretty neutral. But if you rub this balloon on it, the electrons from your hair will travel to the balloon. There's something called an electrostatic series that says which way electrons move, whether they would move from the balloon to your hair or your hair to the balloon. And eventually we'll use it, not today. But you just have to trust that these electrons all travel to this balloon. So now, what are you left behind? Okay? Think about what is left. You have this positively charged hair strands. And so the positively charged hairs are repelling each other. They don't like each other because they are all positive. The same charges repel. And luckily you have follicles, but this hair ultimately is trying to leave your head. Right? It's trying to get away from the other ones. So when it's neutral, nothing happens. But by this balloon stealing the electrons and becoming this big glob of negativity, it made this all positive, and they try to get away from each other. All right. Same thing with the sweater. You can see that you can get the balloon to stick to the sweater. Well, that's because the sweater became positive and the balloon became negative. And again, you need to run that simulation so you know what I'm talking about. All right. Now, I keep throwing all these words at you about protons and electrons and positive and negative, and that's all middle school review. But just in case, what you need to remember is that inside the nucleus of an atom are the protons and the neutrons. Neutrons are important, just not for electricity. They're important in chemistry, all right? But we don't care about them because they have no charge. We care about protons. Okay, so the positive are the protons. And we care about the negatives. Those are the electrons. Those negatives, and you represent them with an E and then a superscript negative, they orbit around the nucleus. You probably remember from middle school, 6th grade science, you had to build an atom. And so you would have had to have the protons and the neutrons inside the nucleus, and then these electrons orbiting around it. So the question that you hopefully are maybe starting to see why, it's only the electrons that move back and forth. These protons are stuck. They are inside the nucleus. The only way we can get them out of there is to add a bunch of energy, like a fission bomb. When we're talking electricity, we aren't talking fission bombs where we're splitting nuclei. We're talking, okay, what's something we can use from here and rip away real easily? It's these electrons that are outside of the nucleus. All right, so only electrons are transferred between objects. When you think about wiring, it's only the electrons that are traveling through a wire. Talked about in our thermodynamics unit in Physical Science A. We said metals are great conductors. They're great conductors of thermal energy. They're also great conductors of electricity. It's these electrons that move the thermal energy around. It's them that create the electrical current. All right, so metals are great conductors, obviously, for our purposes here too. So we only get the electrons transferred. The protons are trapped. Okay, they are trapped in the nucleus, so they will not move around. Okay, the protons are trapped in the nucleus. That's a Cl right there. And this whole process creates an imbalance of charge between objects. So in the wintertime, you tend to get a lot of quick little electrical shocks, right? You walk through the living room and you touch a doorknob and it zaps you. You go to shut a car door and you get a quick little jolt. And what's happening is electrons are moving back and forth. So all of a sudden, electrons are jumping to your body, or electrons are left behind in the car seat as you get up and out, and all of a sudden now you're positive, all right? And we'll deal a lot with this, and again, you should be looking at those simulations on Moodle, especially the John Travoltage. Okay, make sure you're familiar with that. And it shows him kind of kicking his leg on the carpet, and you see electrons moving from the carpet up his leg. And that creates the imbalance of charge, so when you touch a doorknob, you discharge the excess. Right? That's the idea of static electricity. Because static, we know, means at rest. So Downy and everybody makes these, Snuggle, I'm trying to think of all the brands, makes fabric softeners and the little dryer sheets. Because you don't use dryer sheets or a fabric softener, when you go to pull clothes out of the dryer, a lot of times the socks are stuck in pants and all kinds of crazy stuff. Because you get an imbalance of charge. Electrons are donated back and forth. Something becomes more positive, something becomes more negative, and now they are stuck together. All right, so this process creates static electricity, but no matter what, we see the conservation of charge hold true. So what conservation of charge says is that electrons are transferred, so you can move them between objects just like we can move energy around. So they are transferred, but the total number stays constant. We can't just produce an electron. We can't just produce a proton. Okay? Those were there since the heavily accepted Big Bang Theory. Right? Those were generated then. We're not making new protons. We're not making new electrons. We're just moving stuff around. All right? A quick helpful hint, don't mix these two up. Okay, the law of electric charges just predicts what attracts and repels. Conservation of charge says total amount stays constant. That's a common misconception and a common error on LT1. And that is all. Good luck.